Thank you very much. It's really an honor for me to receive this invitation, and I'm very happy to be here today with you. So, without any further delay, I will start with my presentation. The title is Accelerating the Solution of Parametrized Partial Differential Equations Using Machine Learning Tools. And the outline of this presentation is the following. I will start with a brief introduction to explain the motivation behind this work. And then I will present you a surrogate modeling technique that we propose for complex systems using convolutional autoencoders. And two applications will be given regarding the bergers equation, which is actually an illustrative one, a simple one. And then we will apply the proposed methodology to the stochastic seismic response of a steel building. The next part of this presentation will be on how to accelerate the convergence of the algebraic multigrid method using machine learning tools. Is the WebEx window blocking the presentation, or is it okay? Let's move it here. So, as you all know, partial differential equations are ubiquitous in engineering and physical sciences. So, we have the Navier-Stokes equation for fluid flows. We have the equations of 3D elasticity, heat transfer, electrical conduction, and so on and so forth. So, most of these PDEs cannot be solved analytically. And what we do in practice is we use numerical techniques to obtain approximate solutions. And these numerical techniques involve the finite element method, finite difference methods, finite volume methods, isogeometric, etc. So I will mostly focus on finite element methods because these are the ones that I'm more familiar with. And without getting into too much specifics, the idea is that we have a body occupying a domain omega, and we make a partition into finite elements. We discretize it into a set of nodes and edges. And what we try to do is find the values of the field that we want to solve for. We find its values at the nodal points using the finite element method. So, in essence, what we do is we take the partial differential equation, which is an object that is difficult to handle computationally, and using the finite element method, we either convert it into a linear system of D equations, D being the number of degrees of freedom in the problem, which is for a steady state or static case, or we can have a linear system of D equations that we need to solve for its time in a dynamic, its time instant in a transient problem. So computers excel nowadays at solving linear systems, and that's one way to tackle them using finite element methods. But I guess it's pretty much the same with finite difference or finite volumes. No changes here in this idea. So the problems start to arise when we have a very detailed finite element model. And with detailed, I mean that we have a very large number of degrees of freedom. And in such cases, if we were to find our solution, which is the U here, and this could be achieved by inverting this matrix K, taking the inverse of the matrix and multiplying it by the right-hand side to get our solution, our response. And this can be a costly operation if we have a very large matrix K. Now, if we have a transient problem, essentially we have to perform this operation for many time steps. And we see how this computational cost starts to scale. If in addition we also want to solve a nonlinear problem, a nonlinear transient problem, then at each time step we also need to perform a number of Newton-Raphson iterations to linearize it. Again, the cost of solving the PDE now scales even more. But now I would like to make matters worse here and also assume that our system is also parameterized by a vector of parameters theta. So this could be a multicure scenario. These scenarios could be, for instance, uncertainty quantification, optimization problems, Bayesian parameter inference, optimal control, sensitivity analysis, etc. So in these cases, there is actually one way to tackle all these problems, and it's pretty straightforward. We just need to perform a large number of model simulations. For instance, in uncertainty quantification, we have Monte Carlo simulation. For optimization, we have genetic algorithm that, of course, needs model evaluations. In Bayesian parameter inference, we have Markov chain Monte Carlo. So in these cases, we need to solve our complex partial differential equation a large number of times. It could be a massive number, depending on the problem. So we can see that if the cost of one simulation ranges from, say, minutes maybe to hours, then the cost of performing these types of analysis would be prohibitive, unaffordable. And to tackle this problem, we could either resort to high-performance computing, and maybe in a few years to quantum computing. But an alternative approach is to use surrogate modeling techniques, which is the approach that I endorse here. I also focus mostly on Monte Carlo simulation, and just to tell you the idea, the basic idea, we have a set of random variables for our problem, and they follow a specific probability density function, a specific distribution. And the idea in Monte Carlo is to take samples from the distributions of the random variables, feed them to our computational model, the finite element here, perform the analysis, and then collect the results, the solutions, and statistically post-process them after the procedure to get to extract the statistics of the either quantities of interest or whichever response quantities one might need. So in a general setting, let me show you an idea for surrogate modeling. Let us consider the form of a PDE where we can have any differential operator nu here. It can be any differential, linear or nonlinear. U is our field of interest with some boundary and initial conditions. So this is a very generic way to write PDEs. So what I suggest here is that we can take a reduced number of parameter realizations, insert them into the PDE, the partial differential equation, solve the PDE with a numerical technique, in this case, finite element methods. And what we get for each parameter combination, we get our solution matrix, the values, that is, the values of the field at the nodal points of our finite element mesh. And it most probably will be the case that this solution matrix will be of high dimensionality. D here is the degrees of freedom in the finite element discretization, and n sub t is the number of time steps for our transient problem. So these are high dimensional objects, and it's difficult to work with them and building machine learning, use them to build machine learning algorithms. So what we can do is we can train a convolutional autoencoder which will somehow learn how to take these high dimensional objects, compress them into smaller versions, into vectors in particular, which are these zi here. It will learn this process through the encoder, and then the convolutional autoencoder also learns how to do the reverse. Take these low-dimensional vector representations of our high-dimensional objects and reconstruct them through the decoder mapping. This is done in an unsupervised learning fashion, where the convolutional autoencoder tries, after this procedure, tries to minimize the error between our input matrix and our reconstructed matrix. So this way, we can associate a vector representation to its high-dimensional matrix. But then this would facilitate the training of a simple feed-forward neural network that will take as input parameter values from the problem's parametric space, which won't be of high dimensionality, of course. And these parameters, the neural network will learn how to map these parameters to the encoded vector representations. This is so by using z here instead of the matrices u, we somehow circumvent the curse of dimensionality. So this is the offline phase of our surrogate modeling strategy. And the online phase goes as follows. For every new parameter value that was not in the original dataset, we can take this parameter and using the previously trained feed-forward neural network, we can get its representation in the encoded space, this Z here. But then the decoder from the previously trained convolutional autoencoder takes these parameters and maps them to the actual high-dimensional solution space. But this has to be compared with the the original approach, which would be to take this parameter here and perform a time history analysis to get the solution. This approach here will require a lot of time, but this route is associated with almost no computational cost. It's just some function evaluations. I mean, no matrix inversions, no nothing. So it's very fast. The question is to see if it is also accurate. So for a first rather illustrative example, we'd like to review the bergers equation, the one-dimensional bergers equation. And the stochasticity here comes from this viscosity parameter nu, which is assumed to follow a uniform distribution between 0 and 1. And the surrogate building process goes as follows. We start by drawing 100 values of nu from their distribution, from the uniform distribution. And for each value, we solve the corresponding partial differential equation with our finite element solver. So for the finite element discretization, for this problem, we had 200 points in the spatial domain and 100 steps in the temporal domain. And for each simulation, for each model evaluation, we get a solution matrix, this bold symbol U here. And each matrix has dimensions 200 times 100. It's rather big. It's not massive, but it's rather big. And this is the solution matrix of its parameter evaluation. Now, we will train a convolutional autoencoder using these U matrices here as the dataset. And this is the architecture of the selected autoencoder. We mostly use convolutional, actually we use exclusively 1D convolutional layers. And regarding the choices on the number of filters, the pooling layers and stuff, in fact, there was no recipe or guidelines, so it was the result of a trial and error, an experimentation process. And we found that this particular architecture was easy to train in the sense that it involved a tractable number, a small number of trainable parameters, and as I will show you, it will give us good results. So this procedure will learn how to take a matrix of dimension 200 times 100 and convert it into a vector, compress it actually into a vector of dimension 8. And then the decoder will learn how to take this vector and do the reverse operation, give me back my original matrix. So, having trained the autoencoder, the next step is to train a feedforward neural network that will learn how to map the parameters nu I, its new parameter value, to its latent vector representation z. And then the surrogate becomes the composition of the feedforward neural network with the decoder. So, let me show you some results. In the figures that I'm about to show you, we compare the exact model, which is the finite element model, with the predictions of the surrogate model. This is a case for a value of nu, the viscosity equal to 0.2, but of course this was not in the original training dataset. And we see that the exact and the surrogate are in a near perfect match here. We could also take the mean value of our field from the finite element model and the surrogate, and the same for the variance. And we notice that they are in a very good agreement as well. And a more demanding analysis will be to take, for this stochastic problem, to take the probability density functions given by the exact model and by the surrogate and see if these two match. And this analysis will require a number of 300,000 simulations, is a good estimate to get accurate results. And here you see, as you can see, the surrogate and the exact are, their agreement is satisfactory. Now, to get a feeling how the accuracy of the surrogate fares with respect to the dimension of the latent space and the number of initial model evaluations, we see that if we increase the latent space dimension, we can get even better results. And of course, if we also increase the initial model evaluations, the predictive capabilities of the surrogate also improve. And the error, as you can see, reaches values below, maybe below 2%, which is satisfactory. Now, on a more demanding application, we wanted to apply this methodology to the stochastic seismic response of a steel building. And we have an earthquake excitation for this problem. The earthquake excitation is selected as a superposition, actually a random superposition of two existing ground motion histories. And this problem has 360 degrees of freedom, and the earthquake is applied using 2,400 time steps. But also in this problem, we have material and geometric nonlinearity, large displacements and P delta effects. And the material, we have also plastic hinges. So the random parameters of this problem is the modulus of elasticity of the steel members here, their yield strength, they both follow a normal distribution. And we also have this parameter alpha here, which refers to the superposition of the ground motion histories. And we have to start building our surrogate, we perform 400 simulations for different combinations, for different realizations of these parameter values. So actually, this case was a bit problematic because in structural analysis, each node in the finite element mesh, each node corresponds to, is associated to 6 degrees of freedom. There are 3 translational degrees of freedom and 3 rotational. And these can be quite different in terms of their response. So using a single convolutional autoencoder and feedforward neural network didn't provide accurate results. Instead, in this case, we subdivided the solution matrices of the structure into sub-matrices according to the DOF type, according to the degrees of freedom. We have sub-matrices regarding the solution, for instance, of the translational degrees of freedom along the x direction, and the same for the rest. And for each of these sub-matrices, we trained a separate convolutional autoencoder and feed-forward neural network. So in essence, we applied the methodology that I previously mentioned 6 times. But after that, after the training, the online procedure is the same. A new parameter realization is mapped using the corresponding feed-forward neural network to the encoded space, and then the decoder from the convolutional autoencoder maps it back to the solution space. So this is an almost no-cost procedure. And we avoid, of course, performing time history analysis. Now, for all these cases, we considered this architecture for our convolutional autoencoder. Again, we avoided using two-dimensional filters because they would require a lot of parameters and it will make training very demanding. So each matrix of dimensions 60 times 2400 is converted into a 64-dimensional vector. Again, this was the result of a trial and error process. We noticed that it gives very small errors, so that's how we chose it. And this is the architecture for the feed-forward neural network. And now let me show you some comparisons between the exact model and the surrogate. These are, again, for a triplet of parameters that was not in the original dataset. And I don't know if these lines are easy to see, but they are in very good agreement, near perfect, I would say. We can also plot the mean value. Actually, These time histories refer to a specific degree of freedom, a monitored degree of freedom that we arbitrarily chose to illustrate. Actually, it's this node here is the monitored node for the results that I'm showing, but same results are also for other nodes. We get the mean value and variance of the displacement along the x direction, and the same for the rotation. In all cases, we see that surrogate and exact are pretty close. And these are some, we chose some triplets of parameters here that would correspond to more, let's say, rare events. I mean, these are triplets that are far away from the mean value of the parameters, and to see if our model can also give accurate predictions, our surrogate, for the displacement along the x-axis and the displacement along the y. So with the exception of this figure here, all other results show that the surrogate is adequately accurate. Again, the comment here is that the accuracy of the surrogate increases as we increase the dimension of the latent vector, the latent space, and it also, the accuracy increases, the error decreases as we increase the number of initial model evaluations that we use for training. And in terms of computational gain, if we take into account the time that it required to obtain the training simulations and to train the convolutional autoencoders and the neural I present you here these two plots. If we were to perform 3,000 Monte Carlo simulations using the finite element model, the exact, let's say, model, this is the time that it would take. But using the surrogate, this is the amount of time that we would have required. But the gain, if we were only to perform 3,000 Monte Carlo simulation, is not significant. But if we wanted a more detailed analysis and to perform 200,000 Monte Carlo simulations, for instance, to extract partial probability density functions, then we see that the cost, the computational gain would be tremendous to use this surrogate. And now I would like to move, and yeah, it won't take very long. I would like to move to the next topic of discussion, because from what I've shown you so far, the surrogate is very fast in terms of giving new predictions, and it can be very accurate, but it can never be perfect. I mean, there will still be an error. It might be small, say 1 or 2, 3, 5, 4%, something like that, which might be acceptable, but it will never be perfect. So what we are currently working on right now is to find a way to improve the surrogate's predictions. And the idea is here to use as a starting point the surrogate's predictions, and using an iterative solver from linear algebra, and in particular here we will focus on the algebraic multigrid method, iteratively refine the surrogate's predictions until we reach a level of accuracy that meets the purposes of our analysis. So I will start by saying that, as I mentioned, the cost of inverting the matrix of our linear system can be quite costly. And that's why direct methods are avoided for solving these linear systems. and iterative solvers are preferred. This can be Cholesky decomposition, Gauss-Seidel, conjugate gradient methods, and of course the algebraic multigrid method. So the idea of an iterative solver is to start by assuming an initial solution and perform a series of iterations until it reaches the exact solution, exact in the sense that the discrepancy here, this error norm here, is below a prescribed level, level of tolerance. So, okay, this slide is a bit overwhelming. I will simply say the idea of algebraic multigrid. We start by considering our problem in this fine discretization, and we start by performing a few iterations of maybe a Gauss-Seidel or a weighted Jacobi type, and this is called the smoothing. But after a number of iterations, smoothing isn't very efficient anymore, because it's good at eliminating high frequency errors, and at some point the smoothness of the error makes it very difficult to do significant improvements. So then after these few say Gauss-Seidel iterations, we take the residual equation and project it into a coarser mesh using a restriction operator. So we have a coarser problem, and again we can perform an additional number of Gauss-Seidel iterations here to get a better estimate, and we can restrict it to an even coarser level, into an even smaller problem, which can now be solved directly without cost, and get the solution, which is then a prolongation operator maps it back to the one level finer grid, and another prolongation maps it to our original fine grid. So Gauss-Seidel smoothing is involved in several of these levels, but altogether this process can be seen as one iteration of the AMG. This is one cycle of the AMG method, and it's an iterative solver that requires no expensive matrix inversions. So the accuracy of the AMG method depends on three things. In my regard, it's the choice of the restriction and prolongation operator, how to choose them, the choice of the smoothing scheme, Gauss-Seidel or weighted Jacobi or whatever, and on the initial solutions, which is, if you have a good initial solution, it will take less time, less iterations to converge. So regarding the first two, we think, because in essence, multigrid is pretty similar to an autoencoder. Maybe this could be improved using autoencoders, but it's a later work. At the moment, we test to see if we can take the surrogate predictions as the initial solution for our multigrid scheme, and see what gains we can have. Just an application that we are using as our benchmark. This is a two-dimensional plane stress problem with 4 random variables, the loads, these loads here, and the modules of elasticity and the Poisson ratio. And if we were to use the algebraic multigrid method with the initial solution to be the zeroth vector, it will require a number of 536 iterations. But if we were to use in the same multigrid method the prediction from the surrogate, as I mentioned in the previous slides, we would drop this number of iterations. This is actually the mean value of iterations for several individual analyses. The mean value of iterations would be 215, which is a good gain, I guess. So this concludes my presentation, and to conclude, in this presentation, I have discussed about a novel surrogate modeling technique for the solution of parametrized transient PDEs using feedforward neural networks and convolutional autoencoders. The results exhibited high accuracy, even for the nonlinear problem of the high nonlinear problem of the steel building. And it's applicable, this methodology is applicable to methods that require multiple model evaluations. I demonstrated in the context of Monte Carlo simulations, but I guess it could easily be applied in optimization problems or Bayesian inference or anything. Yeah, and the last thing is that we are now investigating how to combine our approach with iterative solvers from linear algebra so as to accelerate the convergence of the solvers in order to have something that it will not only give good predictions in just numbers, I mean, it will also converge to the values that satisfy the partial differential equations of the problem. So, thank you very much for your time and attention, and I would also like to thank my collaborator in these works, Stefanos Nikolopoulos, who is a PhD candidate from Greece.
Thank you so much, Ioannis, for the presentation. So I'm opening the discussion part. Everybody who wants to talk, just switch on your mic or camera.
Can I go ahead, Jakub?
So, okay, we have two candidates. So first Sorab, then I can see who.
Okay.
First Sorab.
Yeah. Hi. Thanks for the presentation. It was really nice. I like the idea of using this latent space vector to reduce the training time. But can you please go to the slide? I'm a bit confused that what exactly do you use to train this autoencoder part, because the input to this is the finite element solution, and for the output you use something u tilde, and I could not exactly understand what that stands for.
So yeah, this UI here is a finite element solution corresponding to the inline, and this u tilde I here is actually the same thing. The convolutional autoencoder must learn how to take the UI input and give me another UI that's pretty much the same. These two must be the same.
But then how do you train it then? It's a bit confusing if it's the same. And what's the training data you use to train this autoencoder then?
No, the training, the loss function here is the norm between this UI and this u tilde I. So the sum of the difference between UI and u tilde. So I don't give this as an input or whatever. It must find through the training process, it must adjust the trainable parameters so that the tilde that it would output here, the u tilde, would be very close to the one that I gave it as input. So,
okay. still a bit confusing for me. Maybe I should get back to you later on this. But
I don't think I have a loss function.
But if we go from the start, I get, okay, you start with some parameters and then you generate the solutions using finite elements. Now you want to use this solution UI to somehow learn ZI and then use this theta i's and Z i's to train the later part so that you save some time in doing new prediction using just this decoder part. Okay, I'm just speaking out my mind, but still, the second step, it kind of puzzles me still.
This part here.
Yeah, the train of autoencoder.
Yeah, this is so this is the only thing that I give as input to the autoencoder, the only thing. And I also define an architecture, say, where will you have the convolutional layers, the average pooling or whatever. And I tell him to do the training on its own, so that what at the end of this process, if you adjust all the trainable parameters here, what you will give me here will be very close to what I originally gave you. This is an unsupervised fashion scheme.
Okay.
Just I just give him this, specify this on my own, and I tell him, computer, do the rest. You will find a way. You will tune these filters, the weights of the filters and the parameters here, and that I want you to give me something that is as close as to what I originally gave you.
Okay, thanks. And another thing you mentioned about the algebraic multigrid methods is nice because this is something also Jakub was quite interested in working on. So I see that you basically initialize the solution with the autoencoder solution. So then you somehow manage two architectures to follow a very similar trend, and you also give the solution value of intermediate layers to this matrices which you get after using restrictions and prolongations. Is that right?
No, actually, this is at a very earlier level at that. I just give the surrogates predictions here at this level and as my initial solution. And then for the rest, I don't have, I started from zero. I don't have any knowledge.
Okay.
But yeah, it's true what you're saying. Maybe we could do the same for the intermediate layers. And but so far we haven't been able to find a way. It's just here. Just take the surrogate prediction, pass it through a few cycles, and make it improve it.
Okay.
Yeah.
Okay, thanks a lot. And if you have any manuscript describing this work, would love to go through it.
Yes, yes. I have actually, regarding this latter part here, accelerating the convergence, there is a very recent paper a few days ago that it was published in Journal of Computational Physics.
Okay.
And this paper tackles these two things here, which is more important than just taking the initial solutions that I showed you. This uses CNNs, convolutional neural networks, to build the restriction, interpolation, and the smoothing schemes in the AMG. I can also give you that. I mean, I'm also reading it right now.
Oh, okay, I would love that. Thanks a lot.
Well, thank you.
Thank you.
Okay, Wolf, you wanted to ask a question.
Oh, okay. Thank you very much for your presentation. I have two questions, and one question is the same as Saurabh already asked. So I asked the other question about when you training separately UX, UI, UX, UI, UZ, and R, like the six separate component when you training for the semantic. Yes, that part. And in this here, you train six separate CAE, I, think the degree, this 6 degree of freedom must be related together. So do you have any method to make the information into play? Because here I just say these 6 separate
Yes,
structure cannot have any related to each other. They are independent.
yes, you're right. You're right. These are independent here with this approach. Maybe we should have a way to relate them, but just as an interpolation scheme, it works like that. I mean, we didn't want to couple these degrees of freedom, although it would be physically consistent, and you're right. But when training the autoencoders, we noticed that the different behaviors between UX and UI, or the rotational degrees of freedom, they made it very difficult for the training process. So just by separating them, of course, we lose the coupling between them, but in terms of the predictions that we get, it worked well. It worked well. But yeah, the coupling is lost.
I got it. It's like you already try to coupling them, but the performance is not as good as independent.
Yes, exactly.
Okay. So thank you.
Can I say something on this slide?
Yeah.
Okay, this is something very similar we tried to do recently to use a autoencoder kind of network to basically relate the force displacement mapping. And what we did was, so we have 3 degrees of freedom for a 3D problem, and we just place this in different channels, and then we use the same network. But all these, let's say UX, UI, UZ, and RX, they are placed in separate channels. We reshape them such that they belong to different channels, and then we apply the filters on them.
And is it faster in terms of training?
Yeah, okay. I can't exactly compare that because we did not try alternate training options, but in terms of accuracy, we think that it gives good results.
Okay, yeah, I see. Yeah, it's also very nice. Nice idea.
Okay.
The thing here that we tried, and we also have as a side project, is how to use recurrent neural networks for transient response analysis. But what we haven't worked through is the problems with also parameters, this theta here. How do I insert them in a recurrent neural network? I mean, intuitively, a recurrent neural network will do the process of autoencoders better, but we can't handle the parameters here.
Okay.
As of the moment. But just saying it for the sake of the discussion.
Thank you.
You're welcome. Thank you.
Can I ask something,
Yes.
Jakub? Okay.
Sure, go ahead.
So, Yanni Kalimera. It
Kalimera.
is so nice to see you again after so much time. I really enjoyed your talk.
Thank you.
I have 2 questions. The first one has to do with time. So when your model gives the prediction, it gives the prediction of the whole time series. Have I understood correctly?
Yes, exactly. It gives us the
Okay.
whole time series. So it's
Oh,
not.
so
Mhm.
yeah.
Yeah. Please continue. Sorry.
So for this to happen, do all the simulations that you use for training, they have to happen within the same time period and with the same time steps, right?
Yes, exactly.
Do you find that this is a bit, let's say, restricting, because maybe some parameter values require more time than others?
Yes, that's actually, yeah, that's a very nice observation. And I know your background and the PDEs that you have in mind, and which is a real issue there. Yeah, for these particular cases in structural mechanics, that wasn't really an issue. We have the earthquake in a given time steps. It's given in a already known increments. But in general, if we didn't have the same temporal discretization, maybe we should somehow interpolate between different samples, I guess. Yeah, but at the moment, yeah, all the matrices here that I've shown you have the same dimensions in time. Yeah.
Okay. So this is nice and convenient. The second thing I would like to ask, since I know you have a huge background in nonlinear manifold learning techniques, and you have done a lot of work on that together with Professor Papadopoulos. How would you comment on the comparison between using those methodologies to the neural network-based methods?
I also know that I have to know that you have also a very huge background in diffusion maps algorithms. And the thing is, before we started working with autoencoders, our idea was to use diffusion maps. But it turns out our conclusion from our investigation with Stefanos primarily, we realized that diffusion maps are difficult to handle, while convolutional autoencoders do the same thing with diffusion maps. They give you nonlinear dimensionality reduction, and the most favorable thing is that they give you the decoder, and this made our lives so much easier. Because with the diffusion maps, the inverse problem was that made, I would say, my life, maybe yours at some point, a bit miserable. The reverse map here is the one that it's not easy to build. But convolutional autoencoders, plus the fact that they are already implemented in TensorFlow, or maybe TensorFlow is what we use, but I guess Python is the same. They are already GPU accelerated, and they are also very powerful. You may need to play a bit with the layers and architectures and stuff, but it's fast to train them, and they are very powerful. I would highly recommend.
Just a small comment from you also, because you are aware of both methods. The number of samples required to have a well-trained neural network versus the nonlinear manifold learning approach. Is it the same? Is it different? Can you comment on that?
No, this is a difficult question, and I only have the image from this experimentation here. I think if I also add into the equation the number of initial samples, I would still say that convolutional autoencoders are preferable over.
They require less, you think?
Yeah, I think that they would require less, but this is a difficult discussion because it depends on the architecture here that one uses. It's very difficult to say a general comment, but I can say my intuition that I would always prefer this route here if I want to make dimensionality reduction.
Okay. Thank you, and maybe we will talk afterwards.
Yeah, thank you.
Nice to see you again.
It's nice to, yeah, maybe if you have time, talk later to catch up.
Hello.
Hello.
Yeah, I also have a question. At first, thanks for your presentation. I read a paper. I think the methodology is very similar to your work. One difference I found in your research, between your research and the paper I read, is the third step.
The third step here.
Yeah, the third step here. Exactly. On this page, in the paper I read, when they train the feed-forward neural network, the input theta I here also including the time. Okay, and in your case, according to my understanding, here theta I is only the parameter space, but time is not included. And then you get your zi, then you use zi input to your decoder, and then recover your high fidelity solution, and then you do the time history analysis. Right, this is your procedure. So if time is in the input of the FFNN, I think it's very simple to, very easy to understand how finally you recover your high fidelity solution.
I'm sorry.
But here, you use the time history analysis. I don't know how exactly you do it. I mean, after you get the I and then you do the time history analysis, what is time history analysis in your methodology?
So sorry, I somehow lost the last part due to a problem with the sound. But
my question is mainly about the time history analysis. I don't know how you finally get your high fidelity solution along the time.
Yeah, along the time. Probably and most likely, the paper that you're referring, maybe they use this approach for real-time simulation, that they get a response at different time steps.
Yeah.
Possibly, yeah. This is, yeah. But what we do here, what we need here is to take the complete response for all time histories, for all time instants, for a given parameter. So time is actually this matrix here. It has all time steps, all responses at all time steps in here. So in this regard, this approach wouldn't be able to perform real-time simulation, in the sense that you tell me the response at time t, and I give you time t plus 1. It gives you the complete solution time history for a given parameter value, and this can be applied for uncertainty quantification, for instance, for Monte Carlo simulation, where we just need this final result here. But real-time prediction, it wouldn't be capable to do with this format here.
Finally, if I already get the surrogate model you mentioned here, and then your model can predict the result between, for example, 0 second to 1 second, and I give you 0.5 second. I want to know the result of at 0.5 second. Your model cannot give me the result in real time.
No, it cannot do that.
Okay.
And that's why I also said, I mentioned actually that we are trying to do this thing that you are saying right now, which is of course a more difficult problem, and we are trying to do with recurrent neural networks, because I've also, there are papers using temporal convolutional autoencoders and maybe some variation. As you mentioned, you could give time t here as the input.
Yes, I think the paper I read, the first two steps almost the same, but in the third step, they add time instead of I.
Okay, yeah. At the time that it took almost 1.5 years for this publication. At that time, we had in mind that we want to make Monte Carlo simulation faster. So we wouldn't need the response to be evaluated at each time instant. we were content with having the full matrix at each new parameter value. But yeah, this is a very interesting problem that you are mentioning.
Okay, thank you.
Thank you very much.
Hello, Ioannis. I am Vasilis. I have a quick question if we have time, Jakub.
Go ahead.
No, thank you very much for your presentation. It was really informative, and I am working with surrogate models for finite elements using neural networks as well. And I had a question. So your parameter space theta, does it include any geometric parameters? So like theta is that, does it relate somehow to the geometry that you have or not?
No.
No. So you cannot generalize over different structures. If I give you a different structure than the one that you had all your simulations, you cannot predict anything about this new structure.
Let me think about it for a moment. I mean, for the cases here, theta was related to material parameters or loading conditions. Okay. But if you're saying that maybe I could parameterize the geometry of the problem, right?
Somehow, yes.
Yes. I think that if this theta is not a very large number, I mean, vector is not too huge to start hitting walls again with the curse of dimensionality, maybe it would be feasible.
Okay. I see.
Yeah, it could possibly require a large number of initial samples for the training. Maybe that's if it's too complex. Behavioral.
I see your point. And how many simulations have you performed now for this analysis? For any of the ones that you showed us?
For the steel building, we performed 400 simulations.
400 simulations. Okay. And is it possible, like, have you made any comparison with like a very, very simple, naive linear interpolation among these 400 examples to see how well it generalizes? Like to compare that with your approach, which is more complicated and will definitely give better results, just to see what you can get with just a very, very simple linear interpolation.
To be honest, no, I haven't.
Okay, just a question, I was curious.
Yeah, but trying to see because I think we just tested linear autoencoders at some point because we want to see if they were better than principal component analysis or something in this fashion, and we couldn't match input and we couldn't match very well input and output. But in general, yes, maybe no, I haven't tested a linear model, to be honest. No.
Okay. Thank you very much. It was a very interesting presentation.
Thank you as well.
Okay, so maybe I'll just take over the discussion now because we should be slowly finishing. So just a general comment that I want to add on the top of what we thought is that I think this idea that you showed, even though it was applied to some engineering problems, I think it is a more general applicability. I think it's in general, this convolutional neural network came from the computer graphics and then now are applied also to somehow encode and decode the results of the finite element simulations. But probably it is also applicable to some more general data that have some geometrical interpretation, and even maybe for graph data as well. So probably this can be applied to social sciences and other applications as well. So thank you so much, Ioannis, for your effort for presenting us your topic. I hope that there will be a kind of follow-up interaction with the people who are interested in your topic. And the presentation has been recorded, so it will be available for future listeners. And thank you, everybody, for your.
Thank you all for having me here today and for your time. Thank you.
So also, let me invite for the seminar in the following weeks. We'll have a very nice series of lectures in the coming few weeks. Prediction of protein structure. So I think it will be very valuable to all of us. Thank you so much again, and have a good day. Bye-bye.
Thank you all. Have a good day.
Thank you. Goodbye. Have a nice day.
Good night.